Audio recording for this meeting has begun.
So again, good morning and good afternoon, everybody, and even to those that are watching, maybe watching during the recording. Welcome to another NICER webcast series, evaluating regional traffic signal performance measures using crowdsourced data in the 2021 Urban Mobility Report. Before I hand it over to our three presenters today, I did want to just do a super brief introduction about each one of them, and then we'll hand it over for the formal remarks. So our first presenter today will be Miss Debbie Albert. Debbie is a associate research engineer with over 20 years of municipal experience. Over her 20-year career, she has also engaged with the public on neighborhood traffic concerns, specific high-profile projects, including a light rail transit line with various city boards and commissions. We also have Mr. Luke Albert. Luke is an associate research engineer with broad experience in traffic operations and transportation engineering. He is a registered professional engineer in Arizona and Texas, and is also a registered professional traffic operations engineer. And then our last presenter today will be Mr. Kartik Jha. He is an associate transportation researcher at TTI in College Station, Texas, where he has been involved with urban mobility measures, freight mobility, project prioritization, and specific event traffic management projects. And prior to joining TTI, Kartik worked as a highway design engineer with design consults in India. And then during his time, he also gained some experience in the project areas of transportation planning, survey optimization, and city transit planning. So with that, I'm going to hand the presentation over to Debbie. So Debbie, I'll change that slide and take it away.
Actually, I think we're going to start off with Luke, so we'll hand it to Luke. How about that?
Oh, I'm sorry. Thank you. Sorry, Luke, go ahead, take it away.
No, thank you, Stephanie. We appreciate the opportunity to talk to you today about our project, which, as Stephanie mentioned, is evaluating regional traffic signal performance using crowdsourced data in the 2021 Urban Mobility Report. And as Stephanie also mentioned, I'll be joined by Kartik Jha and Debbie Albert to present the results of our evaluation. The purpose of this project was to explore a proof of concept to incorporate traffic signal performance into the Urban Mobility Report using the INRIX Traffic Signal Analytics dataset. During this presentation, we'll provide some background about the Urban Mobility Report and then discuss the INRIX dataset and study methodology. Next, we'll discuss the proof of concept for the use of this data for planning level analysis at the corridor, urban area, and statewide levels. And finally, we'll wrap the presentation up by discussing some conclusions from this work. The Urban Mobility Report has a 40-year history of evaluating mobility conditions on freeway and arterial street networks in urban areas throughout the U.S. The report includes 101 intensively studied urban areas with data from 1982 to 2020, and a more recent addition was 393 mostly smaller urban areas that have been studied since 2014. The Urban Mobility Report uses a suite of performance measures mostly related to delay and reliability. Shown in this slide are comparisons between 2019 and 2020 for key performance measures. In general, congestion cost and travel delays in 2020 were about half of 2019 levels. This graph provides some additional context for comparison of traffic patterns throughout the day for 2019 and 2020. Hour of the day is on the x-axis and delays on the y-axis. In 2020, the AM peak disappeared and the PM peak was about half of 2019 levels. In fact, the midday delay was higher than the AM delay, with delay gradually increasing throughout the day. It's helpful to understand these unique traffic patterns because the data used for this project was from 2020. So for this project, INRIX provided 1 week of traffic signal analytics data from October 4th to October 10th, 2020. The data set included approximately 210,000 traffic signals throughout the U.S., and INRIX has since added a lot more signals to their network. The data is obtained from anonymous waypoint breadcrumbs from connected vehicles at 3 to 5 second intervals. And the graphic on the right shows the influence area of an intersection within which vehicles are tracked. Vehicles that are within 150 meters on the upstream approach and 80 meters on the downstream departure are considered to be within the intersection area and travel times calculated. Also, if a vehicle is considered to be stopped if they slow to less than 6 miles per hour, and split failures are determined by vehicles stopping twice or waiting through 2 red lights before clearing the intersection. In addition, a vehicle is considered to be delayed if they're traveling at speeds less than the 5th percentile travel time. This slide shows information about the data that was received from INRIX. 15-minute data was provided, which included 672 15-minute time periods for each traffic signal for the week the data was collected. The intersection coordinates were provided and allowed us to assign each urban intersection to an urban area. The data provided for each 15-minute period included an actual vehicle count and estimated total vehicle count based on the sampling rate that INRIX had. We also received data for the average delay per vehicle, which is the average time spent waiting at an intersection, percent arrivals on green, or percentage of vehicles that were able to proceed through the green light without stopping were also included in the data set. And we received a count of split failures for each 15-minute period. And as I mentioned before, that's just split failures or vehicles that sit through 2 red lights before clearing the intersection. And the level of service for each intersection for each 15-minute period was provided. And level of service is just a report card letter grade assigned to the intersection based on the amount of delay, with A being the least delay and F being the most delay. Some key data considerations are shown on this slide. The sample rate was 2% to 8%, which is a good sample, although it is still a sample and not all the vehicles passing through the intersection. We're also well aware that 2020 was a unique traffic year, so the fact that this data was from 2020 needs to be considered in the analysis. Another consideration is that community goals vary, as some communities promote non-motorized transportation more than others, so community goals need to be considered when comparing urban areas to each other. Network topology also comes into play when comparing urban areas. Some urban areas have a nice grid network that makes timing signals easier than a more random spacing of signals and layout of roads. Lastly, because we looked at 1 week of data, major events can affect traffic performance measures. Weather is an important consideration. For example, there was a hurricane in Louisiana during this time frame, and there's also the potential for October snowfall in the northern U.S. And finally, construction, traffic incidents, and tourism are also considerations. In an effort to minimize the impact of construction, we looked at only weekday data in these analyses, as a lot of major construction traffic impacts in larger urban areas occur on the weekends. The next couple of slides review performance measures that we looked at in our evaluation. Average delay per vehicle, percent arrivals on green, and split failures were directly aggregated from the INRIX data. And percent arrivals on red, which is just the percentage of vehicles that had to stop at the intersection before clearing it, were calculated from percent arrivals on green. And shown here are some additional performance measures that we're piloting as part of this evaluation. Traffic Signal Efficiency Index, or TSCI, can be considered as X times more likely to arrive on green than red. If TSCI is greater than 1, then you're more likely to arrive on green than red. And if TSCI is greater than 2, you're more than twice as likely to arrive on green as red. TSCI is calculated by dividing the percent arrivals on green by the percent arrivals on red. And this is in the same family of measures as the platoon ratio and the highway capacity manual. We've also seen some similar metrics used by local agencies. In an effort to eliminate the impacts that are beyond the control of traffic engineers' timing signals, we calculated an adjusted TSCI that eliminates split failures. Split failures are often caused by items that are outside the control of traffic engineers, such as emergency preemptions and capacity constraints. So adjusted TSCI provides a better representation of the efficiency of signal timing. And lastly, we calculate a weighted level of service. We assign level of service A a value of 1 and counted up to level of service F as the value of 6, and weighted the level of service for each 15-minute period by traffic volume to calculate a weighted level of service for each intersection. This is an index with the lower number representing better level of service. Next, Debbie will talk about the use of this data to evaluate traffic signal performance along a corridor.
All right, thanks, Luke. It's great to be with you all here today. So as part of this analysis, we looked at the performance measures Luke just discussed and applied them at the intersection and corridor level. So now I'm going to just walk you through these next few slides and give some background on how the performance measures were applied so that as we weight and aggregate them to the urban and state level that Kartik will talk about, you have a better understanding of how these pieces fit together. So shown here is a sample corridor we used for illustrative purposes in taking a look at the data from a planning perspective. This stretch of roadway is roughly 7 miles long and includes a total of 22 traffic signals. The east end, the intersections over here, I hope you can see the pointer, intersections 1 and 2, those are a diamond interchange, while on the west end over intersection 22, that's a single point urban interchange. The remaining 19 intersections are a mix of arterials. Those are the A's that you see below all of the different dots. So arterials, collectors are C's, and then D's are the driveway intersections. And the intersections are roughly spaced between 1 quarter and 1 mile apart. So you can see in this graphic, the density of the intersections or signals really start to pick up here starting at intersection number 8 and going west, where we have mostly 1/4 mile spacing versus when you get closer to the east side where we start to see that 1/2 mile and 1 mile spacing of signals. The average ADT on the 6 and 8 lane arterial is between 40 and 60,000 vehicles a day. And then another characteristics of the corridor is that there is a range of different land uses from residential to office to commercial, including some really intense commercial development and a regional mall that are served by these signals on the west end, signals 17 through 21. So based on this, you can start to see kind of some of those effects that land use might have on signal timing. All right, so this table provides the results for each of the intersections that we analyzed. The data obtained directly from INRIX is shown in these purple boxes here. Let's see if I can get my stuff to work. And then the blue boxes are the performance measures that we calculated. Additionally, corridor characteristics such as signal spacing, side street functional classification, and land use are also listed on this graphic. So let's start by looking at the delay and the percent arrival on green. We'll go ahead and zoom in a little bit so that you can see these numbers a little bit better. But as expected, we start to see that the highest delays, those are those longer orange bars in the left column, they're at those arterial intersections. And then here, if you remember, the higher number intersections are those areas where we had that dense commercial activity centers. The least delays are on the collector street intersections and those that typically have residential or light commercial or mixed land uses. The percent arrivals on green, which is in that right column, they tend to follow the same pattern as the delay data, with the exception of this intersection number 20 and down towards the bottom. And this could be because the cross streets are a combination of a collector street and a driveway as opposed to an arterial intersection. And the results are aggregated over all of the weekdays combined. The percent arrivals on red are just the inverse of the arrivals on green and range between 9 and 65%. This is kind of just like looking at, is the glass half full or is the glass half empty when comparing between arrivals on green and arrivals on red. Looking more closely at the split failures, you can see that the split failures, the proportion of vehicles not getting through the intersection on the first green light, they're pretty low for all of the intersections. But keep in mind, again, this is 1 week of data in October when many of the schools were still providing virtual options and a lot of people were still working from home. So there was less traffic demand and shorter lines at the signals. One other thing to point out, though, is that INRIX is not considering vehicles outside that intersection influence area that Luke talked about earlier. So if you have some very long queues, maybe those that are over 150 meters upstream, they are not accounted for in the split failure count. So this value may be artificially low or underestimated. There is, however, an INRIX corridor tool as part of their suite of tools that takes the corridors into consideration when conducting this type of analysis. So the information is available for users. So the low split failures that I just talked about means that the percent arrivals on red that are shown here without the split failures are pretty much the same as I just showed you in a couple boxes ago. And then the two traffic signal efficiency index numbers. So remember, this is a measure of the relative likelihood of arriving on a green versus a red signal indication. They are also about the same with those low split failure rates because there just isn't a lot of split failures to remove. So Luke explained how the index is calculated earlier, but I'm going to give you a couple of quick examples just to give you a sense of how these TSEI values would work. So based on this data, drivers arriving at intersection 13, the way you would interpret this is they're over 9 times more likely to arrive on a green signal versus a red signal. Conversely, a low number, such as the one here on intersection 18, the traffic signal efficiency index is just 0.69, which is less than 1. So drivers are actually more likely to arrive on red than green, and that's nearly 1.5 times more likely to encounter a red than a green. We feel like this is a really good measure to explain to the general traveling public, because when they're starting to try to figure out what is actually happening to them or what they should expect in their own personal experience, you can talk to them on an individual level here. And then finally, the weighted level of service is shown in this column. And in this case, the lower the number, the better the level of service provided, as Luke was mentioning. So level of service is another measure to help tell the story of how a signal is operating. But since the letters cover a range of delays, performance measures like the TSEI provide a little bit more detailed insight for both the traffic engineers and the public on how the intersection is operating for them. All right, so recognizing that traffic patterns and signal operations change throughout the day, we looked a little further into what that might mean for the performance measures. This first chart here is looking at delay. I know it's very busy, so let's go ahead and concentrate on these straight dashed lines in the middle that are shown in the pink box. That black line in the middle here, you can see, let's get my cursor down here. This black line in the middle here, it is the median delay for an overall corridor for the whole day. So not surprising with COVID in 2020, the AM delay, median delay is lower and is showed in the green. So this is much like that graph that you saw from Luke earlier and where he was talking about flattening the curve, the delay curve. And then the mid delay is the orange line. It's slightly above all of the median delay. And then the PM peak corridor delay is at the top in red. So the highest delays are in that PM peak. Now, looking a little bit broader at how the individual intersections perform, the color scheme stays the same, but there are different shapes to help delineate each of the time periods. So we start to see that the delay levels are more spread out throughout the day. You start to get some higher and lower ranges between the AM, PM, and overall delay for the day. And as you travel east, where there are more residential areas, the delay tends to be more constant throughout the day versus, on the west end of the corridor where you've got that intense commercial development and the variation isn't so spread out. So interestingly, we do see a handful of locations where the midday delay is actually larger than the PM peak. So we start to break it down to that time of day period. We see some locations where the midday is higher than PM peak. And these could be locations where people are venturing out to run their errands during the midday or lunch time period. So this graphic contains the same temporal information, but for arrivals on green based on the different time periods. So if you recall from the first signal map that I showed you, that density of the signals really started to pick up after intersection 8. From this graph, we can see the arrivals on green, they really don't seem to be impacted by the more closely spaced intersections. You still get those, the ranges, and you get, some pretty high percentage arrivals on green, even in the more densely populated or densely closely spaced intersections, particularly, in that regional mall area, intersections 17 to 21. There is some pretty good progression between intersections 9 and 17, with the exception of two, number 12 and number 15, which are both arterial street intersections. So in these cases, this cross street may not or may be a higher priority corridor, and that they're actually programmed stops at these locations in your signal timing, or the lower percentage arrivals on green are actually vehicles that are on those cross streets. Our next chart is the traffic signal efficiency index for each intersection. So remember, a 2.0 efficiency index means that you're twice as likely to arrive at an intersection on green versus red. So we're again looking at a measure of coordination with this performance measure. About half of the intersections have an efficiency index above 2.0 for at least one part of the day, showing good coordination. There are even a couple of standout locations, where we're getting an efficiency index of 12 for the AM peak and above 6.0 for the whole day. The majority of the intersections with lower traffic signal efficiency indexes are at the freeway interchanges or arterial streets, where you may have large competing traffic flows, or signal engineers may be trying to balance coordination. Or there may even be more active transportation users at those locations. So interestingly, the indexes at these locations do not seem to change much throughout the day, so over those 3 time periods. This last chart here is the weighted level of service for the corridor as a whole and individual intersections for the different times a day. So since the level of service is a function of delay, it looks very similar to the delay chart I showed you first when we started looking at these series of graphs. So I'm not going to spend a whole lot of time here, but just wanted to show you the realm of possibilities for analyzing the data. There may be some small changes from the delay graphs based on the influence of higher or lower traffic volumes, since this is a weighted level of service and indexed against traffic volumes. So wrapping up on the corridor and intersection proof of concept, we made several observations. First, as expected, there was better signal performance at the collector and driveway intersections compared with the arterial intersections across all those performance measure categories. And again, this could be a function of the operations policies or higher traffic demands at the arterial streets, or even a combination of both. Signal spacing did not appear to affect the signal performance. Additional data outside of that COVID time period, that 1 week of data that we have, may provide some more valuable information on signal density effects though. This data has proven to be another useful tool for traffic and signal engineers to monitor and evaluate their signal performance. This is especially true for urban and suburban areas where corridors regularly would cross agency boundaries or operational control, and there may be varying levels of signal data that's available for this type of analysis. We are working, we're specifically looking at this data and its application for planning purposes. However, it should be noted that the data does not replace your traditional detection equipment that uses for the basic operations of the traffic signal. It's a great supplementary tool that can point out areas where modifications to signal timing may result in improved user experience. So now I'm going to go ahead and turn the presentation over to Kartik to discuss the analysis completed for the urban areas and states, so that you can see how the signal performance measures are captured together in a wider area. So go ahead, Kartik.
Hey, Kartik, don't forget to unmute.
Oh, sorry. All right.
That's okay.
Thank you, Debbie. Can you all hear me now?
Yeah, we have you.
Okay, great. Okay, so thank you, Debbie. Hi, everyone. So what Debbie highlighted up until now is the more disaggregate and granular level at which we have analyzed this data and its utility for application. Now we'll look at a couple of ways in which the same analysis can be applied at a more aggregate level. The first is at the urban area level. As Luke discussed earlier, the UMR tracks mobility performance measures in 494 urban areas, out of which 101 are intensively studied. The evaluation of urban areas in this section of the analysis focused on these 101 areas. All signalized intersections in the INRIX database were geolocated and assigned to urban areas. These same metrics as discussed earlier were calculated for all signalized intersections. Like in the case of analyzing individual intersections and a sample corridor that we just looked at, this analysis also uses just weekday data. So the following few figures chart the data for different calculated metrics for the 97 urban areas among the 101 for which vehicle mobility data at signalized intersections are currently available from INRIX. The entire dataset for all 494 areas included a few urban areas with a very small number of signals in the sample data. Several such urban areas exhibited outlier behavior based on statistical tests, mostly in terms of high delay per vehicle and arrivals on red. After filtering out urban areas with fewer than 10 signals, the behavior was much more consistent among the remaining ones. This filtering process removed 20 urban areas out of the 463 for which INRIX signal data were available. This issue was not at all observed for the 101 urban areas, so no filtering was required in this case. This first chart that you're looking at is for the percent arrivals on red, and we'll see two other metrics on the next two slides. As the direction of the arrow on this graph indicates, a lower position on this chart points to better signal performance. On this chart, we see how the traffic signal efficiency index, the TSEI, varies for different urban areas. Worth emphasizing is that the intent here is not as much on ranking urban areas on their signal operational efficiency as it is to find patterns and interesting tidbits that this data can bring out even at the more aggregate spatial levels. For example, we can see that several college towns appear at the better end of most metrics, which is on the right side of this chart, uh, if you can follow the arrow. So a contributing factor might have been the period of observation, which is in October 2020, when a majority of colleges and universities were operating classes virtually, thus resulting in much lower congestion levels, reduced traffic demand, and better signal operation. Similarly, as we can see on this graph, local or regional priorities with respect to vehicular and non-vehicular traffic and special situations like hurricanes, snow, or bad weather conditions in general, etc., might impact some of the urban areas which emerge at the lower end of most signal metrics. These factors can be local and specific to the time window of data observation, therefore, can be investigated further for a more conclusive identification of causal factors. Now, to delve a little deeper into how some of the external factors might have an effect on signal performance, we explored the effects of three factors: urban area size, which is proxied by population here; secondly, the signal density in that urban area; and finally, the magnitude of total arterial delay in an urban area. It can be expected that some or all of these factors will have some influence on how signals perform, so it is interesting to see how those patterns unfold in recorded probe data. It is observed that the size of urban area does show a mild influence on some of the signal measures. In particular, the range of variation in values gets moderated to some extent with increasing size of urban area. We see that here for the average delay per vehicle. And we observe the same, actually the same observation for traffic signal efficiency index on this chart, where the range of values is wider for small and mid-sized urban areas, while the range gets tighter or more compressed for larger urban areas. You may infer that there is a slight negative slope here. In other words, the efficiency index drops a bit with increasing size of urban area, but the effect is hardly there or mild at best, which is another interesting observation. The weighted level of service typically tends to get worse which you can see in the higher number of values, and as we repeated a couple of times, the higher the number for weighted LOS, the worse the traffic conditions or signal operations are. So it gets worse for larger areas compared to smaller urban areas, accompanied by a reduction in the spread or the range of values. But as with the metrics already seen, the couple of metrics we saw, the impact on actual values is not as pronounced as it is as on the range of values. There is a mild slope on all the graphs, but the more significant effect is on the range of values getting narrower with increasing urban area size. On similar lines, signal density and magnitude of total arterial delay in an urban area were also used as classification factors to examine their impacts on the values of signal metrics. Signal density was calculated as the total number of signals in that urban area divided by the total arterial cell turn miles. Total arterial delay was calculated by the Urban Mobility Report methodology, the UR methodology. As this chart shows, the average delay per vehicle does not change appreciably with increasing signal density in an urban area. The inference doesn't change if we use the total arterial delay in an urban area as a classifier. These observations can be attributed to the fact that urban areas with higher signal density and arterial delay are usually the larger, more resource-rich areas where signals operate at a network as a network rather than as isolated intersections. Therefore, the effect of higher demand or the level of traffic is offset to some extent by typically better utilization of more resources such as funds, signal timing personnel, plan, routine, etc. Interestingly, percent arrivals on green improves with higher signal density in an urban area. This follows from the previous observation that an urban area with higher signal density tends to coordinate their operation and devotes more resources to keeping those signals well timed and coordinated so as to allow a better progression of vehicles arriving at an intersection. Consequently, the traffic signal efficiency index improves as signal density or arterial delay increases. Similar to average delay per vehicle, the traffic signal weighted LOS, the level of service, does not show a definitive pattern with increasing signal density. It can be attributed to the same logic as for average delay, which is better, more intentional operations and use of resources by areas with higher signal density. To summarize the results for urban area evaluation, the average delay per vehicle does show an increase with urban area size, but more significantly, the range of signal performance is wider for smaller urban areas and tighter for larger urban areas. As we saw, the percent arrivals on green increased with a higher signal density, mostly attributable to the better operations and use of typically more resources available for disposal in areas with higher signal density. And finally, as alluded to earlier in the discussion, local or regional priorities and special or severe weather conditions can have an effect on calculated signal metrics, particularly considering the small time window, which is just 1 week of data collected and used. At the most aggregate level, traffic signal operation performance measures were also evaluated at the statewide level, including District of Columbia. Although this might not be the best suited use of signal data in its current state, it still provides some context to operational metrics at an aggregate level for trend monitoring, which can be investigated further at a more granular level depending on use case and scope of application. The following few charts show the variation of a few metrics, percent arrivals on red, which you see here, and then traffic signal efficiency index and the weighted LOS that we'll see later for all the states. Some local or regional factors might be impacting the observations and thus the results for the states. The period of observation is short, just 1 week, and that is during October 2020, when traffic in some of the northeastern states might be impacted by snow, fall foliage, or other regional conditions, and just COVID in general. These are the results for state-wise evaluations of signal data for the efficiency index, TSEI. This study also examined if using just weekday daytime data which is 5 a.m. to 9 p.m., just daytime, shows significantly different results for the signal metrics compared to all-day traffic data. It was found that using only daytime data did not have a significant impact on the values of calculated metrics. Looking at the results for weighted LOS by state, worth revisiting here is the fact that state and local priorities may dictate the acceptable levels of signal operational metrics. For example, prioritizing bike, pedestrian, or other non-motorized vehicular traffic over vehicular traffic. Let me just say that again. For example, prioritizing bike, pedestrian, or other non-motorized traffic over vehicular traffic may be a desired outcome in particular jurisdiction or location, and an associated moderate degradation in signal metrics may be entirely acceptable, if not desirable. To summarize the statewide findings, obviously, as we discussed, being the most aggregate level of analysis, we lose some granular information when we move from the individual intersection and corridor level to the state level. But still, because the individual intersection data bubble up to become part of all of the more aggregate level numbers at the urban area and state level, these can be useful for a high level look at signal performance to identify need for additional, more granular evaluations from a planning aspect. Secondly, events and priorities can affect statewide performance measures. So in some respect, these metrics can be more useful in capturing the context behind the numbers rather than lending themselves to peer ranking. And finally, we found that just daytime data metrics did not deviate significantly from the all-day metrics. To conclude the findings and contributions of this study, it is found that probe-based data signal analytics is beneficial to evaluation of traditional and newer metrics, more contemporary metrics. These can be seen as a supplement to traditional data collection and evaluation. The need for less direct data collection, equipment maintenance, and data processing makes this a good approach for supplementing traditional signal performance monitoring processes, especially at the planning level. It can provide traffic engineers and signal operations personnel some actionable information at the individual intersection and corridor level, particularly with respect to time of day patterns and signal progression characteristics. It also shows some promise for extracting useful information for tracking and trend monitoring at the urban area level. Finally, it is important to consider variations in community goals and priorities for diverse transportation users while making peer comparisons at the more aggregate, which is at the urban area and state levels of analysis. Just to share some thoughts on future avenues for evaluation, as discussed, we performed these analyses at the intersection, corridor, urban area, and statewide levels. This can be diced up a little more at the level of operating agency because that's where the rubber hits the road. So it can be very useful at that scale. These analyses can provide a good opportunity for periodic tracking and trend monitoring in a more or less automated manner, which can be a precursor to a more detailed look as needed. Evaluations by time of day can be undertaken in the same manner at the area-wide or state level as in the case of individual intersection that we discussed. And finally, network topology can be studied in more depth while contrasting corridors or regions to account for potential effects of a grid network compared to a more unstructured layout of network roadways. With that, on behalf of my team at TTI, I thank you for your time and patience. Happy to take questions now, and we can also be reached out at the contacts provided if you'd like to have a follow-up conversation later. Thank you again, and I will hand it back to Stephanie for the Q&A part of the session. Thank you.
Thank you, Luke, Debbie, and Kartik so much for all the great information on the report. I did want to just remind everybody that we do have about 17 minutes or so for questions and answers. The Q&A box is located on the bottom right-hand corner of your screen. Simply type in any questions or comments that you have. We'll get those read out loud and get the three presenters today to answer those questions. And then just as a reminder, in the files box immediately above the Q&A box, you do have a copy of today's presentation printed in a PDF format. It's 2 slides per page. So if you're only seeing one slide, go ahead and scroll on down to see the remaining slides. So it does look like we have several questions already in that Q&A box that we'll sort of ask one at a time. So let's start with the first one. So this person asks, how would city traffic and engineers benefit from this data?
Stephanie, I can go ahead and take that question. But I think the big thing is, looking at those corridors or regions of an area, allows those traffic engineers to identify not only hotspots, but then also, if they make signal timing changes, they're able to track and identify the benefits or any issues with whatever timing changes they put in place. And then over time, just as policies change within an agency, they can, they can monitor, how the signal performance has changed over time and provide reporting to elected officials or to the community. I don't know if Luke or Cardiff, you guys had anything else to add to that?
I think you answered that well, Debbie. Thank you.
I'll just sort of ask a follow-up question. Do you have any case studies or anything that show how cities have benefited from this data at all? That may be outside of the scope of this work, but
I know
just was wondering.
Yeah, I've attended some INRIX webinars, Stephanie, and they do have cities that are users of this data set as customers, direct customers, and it's even like a more robust version of the data set for the customers, but they certainly have cities that they have that use this data set regularly.
Okay, perfect. The next question comes in. It says, what is the benefit of tracking traffic signal performance at a national level in a report such as the Urban Mobility Report?
I can take a shot at this one, Debbie and Kartik, and y'all can jump in. Yeah, obviously, Debbie showed, obviously this is very useful at the intersection and corridor level, but and then obviously as Kartik then showed, it can also be aggregated up to the highest levels for such as like urban areas or even states for performance monitoring. I think that's helpful for a lot of times MPOs, are looking at like a much broader area than cities are looking at, looking at a whole region. And this data is certainly useful to aggregate up to that level for the region. And then like I said in the UMR, then you can do some comparisons between urban areas. But you just have to be careful, like we mentioned before, about community goals and so forth when you do those comparisons, just to make sure you're really comparing like communities. And then lastly, of course, just that tracking year to year. If you were to use this data set year after year in the same urban areas, you could do some tracking over time there.
Okay, then next question comes in, says, how could this data set be used in the future?
And I can start this again too. Oh, sorry, Kartik, go ahead, Kartik, by all means.
Okay. Yeah, so as we discussed a couple of times during the presentation, I believe that it's great for just trend monitoring and tracking performance over time at many spatial levels, not just at the most granular, but also at the more aggregate levels. And I think that can be a primary use of this data. But also, I feel from a planning perspective, as for I think the first question the city engineer used, I think it can provide more and more granular information that can be used as a precursor rather than the definitive answer, but just as a starting point to look at intersections, corridor, even urban areas at a more detailed level as needed. So I would say, yeah, trend monitoring, tracking performance over time can be a primary use, but also looking at it more closely as a starting point to look at locations more particularly can be a good use of this data in the future. Anything to add, Luke or Debbie?
Yep, I think you
I
got
thought
it
that was
covered
great.
there.
Yes, thanks, Carter.
Yeah, and I would just like to add, I think, yeah, tracking performance, trend monitoring also can, take into account changes in policies or, timing. So if there is a routine change or there's a timing plan change, this should show up in numbers. So that's also something, like a before and after. So if the data penetration increases, reliability of data increases, sample penetration with sample penetration, I think it can be a good tool, a reasonably good tool to get started with, before and after, to look at, uh, patterns, how they evolve over time with, policy changes or timing plan changes.
Okay, we did have another question come in. Was there any consideration of pedestrian and bicycle facilities?
And I can start there too. So, I mean, this is a signal data set that we received. So there wasn't, they weren't like included in the data set or part of the calculations. So it's just something to keep in mind when reviewing this data, that that there's other users that need to be considered. Um, it's just like I said, something you need to consider. But this data set is strictly the vehicles at the traffic signals.
Okay, it doesn't look like we have any additional questions. So I'm going to give you back about 10 minutes of your afternoon. I am going to open up the evaluation for everybody. So please take a few moments to complete that evaluation, as the feedback provided is very important to our presenters today. So thank you so much, Debbie, Luke, and Kartik, for all of the wonderful information. This webinar is recorded. It will take us a couple of days to get the presentation downloaded and posted on YouTube, but it will be available on the NYSER website. So we do have our next webinar, which is scheduled for May 12th. It's corridor monitoring with a UAS, presented by one of our researchers here at the University of South Florida. So on behalf of the National Institute for Congestion Reduction, thank you so much for joining us today, and we'll see you all real soon. Bye, everybody.
Thank you, everyone. Thanks, Stephanie.
Thank you so much.